For this video, we are going to be able to control the position and the velocity of a DC motor. The objective is to create an informative and instructional video tutorial that is going to explain you and demonstrate the concepts and techniques involves the control of this position and velocity. Also, it's a guide to understand and to implement these control methods effectively. So what you can expect is to control the DC motor with a potentiometer, also with the you will understand what is a set point, what is the gain, what is the basics that you need to implement the PID correctly. So the basics that we need to know about this project is how a DC motor works. The DC motor converts electricity into motion using magnets and coils. Okay, so with this in hand, we will need to know some formulas and also theorems that we're going to be working with. One of those is the Kirchhoff law, that is going to help us to know the model of the motor. Also, we're going to use the electromechanics law, that we are going to use it to put all this together. And also we are going to use Euler's formula, that is going to help us to have all this together. We will need to know about the back EMF, that it's like the magnetic field generates a back EMF that opposes the applied voltage. The back EMF is proportional to the speed. So and it's just you just need it to have it in count, but it's not that important. Also, we need to know that in all the motors have a different torque, that it's like it's the turning force produced by the motor, that it's what makes the motor shaft to rotate. Voltage and speed relationship that we have, because if you if you give less voltage to your motor, it's going to be working with a lower speed. And that will be like the basics that we will need to work with this.
Okay, so first, what is control? Control in engineering refers to the set of techniques, methods, and tools used to manipulate, regulate, and maintain the desired behavior of dynamic systems. We can manipulate any kind of system while the system has its mathematical function, whether they are mechanical, electrical, electromechanical, or any other system subject to changes or disturbances. In control, we can manipulate the system adjusting the variables or parameters with the aim of achieving great performance and accuracy. Having a great performance, maintaining stability, following a desired trajectory, or reaching a desired state. We can control system with controllers. There are various control types. We can mention the PID controller, proportional, integral, and derivative control, being one of the most common. PID control adjusts the system output based on the proportion of the current error, the integral of the accumulated error, and the derivative of the error. Position control theory refers to the methods and concepts used to manage and control the position of a system. Often within engineering and control system context, it involves the application of control strategies to maintain or achieve a desired position for a device, machine, or a system. Or in our case, we are going to use velocity and position. Here are the fundamental aspects of position control theory. So, position control theory refers to the methods and concepts used to manage and control the position of a system. It involves the application of control strategies to maintain or achieve a desired position for a device, or in our case, for a motor. Here are the fundamental aspects of the position control theory. First, we can mention the position sensing. So, in our case, the control it needs the ability to sense and measure the position of the system accurately. This can be achieved through various sensors such as encoders, potentiometers, optical sensors, GPS, and so on. In our case, we are going to use encoder, a motor with encoder. In position controller, the control algorithms are employed to process the position, feedback, and generate control signals to adjust the system's actuators or inputs. These algorithms include PID controllers, steady space, adaptive control, and advanced control strategies tailored to the specific requirements of its application. We also can mention the reference or set point. So we are going, the set point is going to be the desired position. So the desired position is the position that our system has to achieve or maintain during the process. And also, the control system works to minimize the difference between the actual position and the set point. We can also mention stability and performance. This is going to be essential for our position control theory, just because we have to maintain stability, avoiding oscillation or instability. And avoiding this, we are going to achieve desired performance criteria, such as a setting time, accuracy, and robustness to disturbances. For setting up our DC motor, we use two principal parameters, our RPMs and our pulses per revolution, and our values per revolution were 788 pulses, and our revolutions per minute were 187. And we also have to mention we obtained these values with coding and with using MATLAB and Arduino. So here we're going to explain our position controller. First, as we can see, we define the number of our pins for our connections in the Arduino, and also we define some variables like the errors, the gains, and so on. Then, if we go more further, we can see in the void ISR encoder, we are going to keep the track of the quantity of changes or movements detected by the encoder. And then, in the void setup, we configure our inputs and our outputs. After that, we only initialize an interrupt on a specific pin, enables serial communication as sets initial output pin states for controller our motor. Then, in the void loop, we configure we assign the current system time value. Then we ask for the number of revolutions, and then we calculate the speed after a certain time pass, in this case 100 milliseconds. After that, we calculate the time elapsed since the last measurement, and finally we update the counter and the time for the next speed measurements. And then we can see we have some variables here, like our derivative error and our integral error. And we have here the formula for our PID controller. And also we have here our set point that it's going to be for our pot. Here we have the analog read input. And then we also have here a condition. If our error is positive, we are going to rotate our motor in one direction, and in the other hand, if our error is negative, we are going to rotate our motor in the opposite direction. And finally, we are going to print our variables, our actual value and our set point. For velocity control theory, we can talk about some principles and methods in engineering control systems. This theory focuses on controlling and maintaining a desired velocity profile or speed for a particular application. So we can talk about, for example, velocity sensing, and this relies on sensors to measure and provide feedback about the actual velocity or the speed of the systems. We can use various sensing technologies such as encoders, tachometers, speed sensor, and so on. In this case, we are going to use encoder. Then we have our reference or set point. The reference or set point is going to be our desired value, our target velocity that we want our system achieve or maintain. This speed is going to be determined by the control system, and the control is going to minimize the error between the actual and the desired value. Then we have also our control algorithms such as PID controller, and this controller is going to control signals and adjust them just on basing on the difference between the actual and the desired velocities. And finally, you can also mention stability and performance. As we mentioned in position controller, we want stability, and this is crucial to ensure that the control system operates without oscillation or instability. We want to regulate the oscillations and also velocity, achieving the desired performance metrics, such as response time, accuracy, abruptness to the services. As we also mentioned, we also use some parameters for velocity controller, as like the revolutions per minute, and also we use the pulses. We obtain these values from some codes from Arduino and MATLAB Simulink. Then we're going to talk about our velocity controller. So it's almost the same as the position controller. First, we also define the number of our pins for our connections in the Arduino. We also define some variables like the errors, the gains, and so on. Also, in the boy ISR encoder, we're going to keep the track also of the quantity of changes of movement detected by the encoder. In the void setup, we also configure our inputs and our output pins, and we only initialize the interrupt on the specific pin, and in order to control our motor. Then in the void loop, we first assign the current system value in millis. Then we ask for the number of revolutions with this formula. Then the program calculates the speed after a certain time passed, and also we calculate the time elapsed since the last measurement. And finally, we update the counter and time for the next speed measurement in order to this value update, and the program can always make the changes. Then also here we define some parameters we need for our formulas for our PID controller. Here we have also the proportional error, also the integral error and the derivative error. And finally, our set point, we're also going to use a pot, and we're also going to change our set point from these values. And yeah, also we're going to print the real velocity and also the desired velocity. And here we're going to show it. And that's it.
The controller that we are going to use in this case, it's a PID controller that will those for each one P, it's only to control like the velocity that it's going to take to move the motor to the set point. Okay, so it's just like the speed, the thing that you're going to need in this case if you only put proportional. The integrator, the KI, it's going to help you to reduce the steady step error. So in the case that you already have the position that you would like, but it's not reaching the set point, it's just like, okay, a line, and you have a line here. So the integrator is going to pull this line together or well near to the other, to your set point. The derivative is only used in the case that you have oscillations, but by itself it doesn't do anything. So you will need to complement it with P gain or an I gain. Okay, well, so first of all, to connect this circuit that we have, we need to know which connections we had in the motor. So in this case, we have that the red cable and the black cable are the ones that we're going to connect to the voltage. So we want this to be connected to that voltage. Also, the green and the blue cable, we are going to need it because it's the encoder. This is the voltage, and this is the ground. The green is the ground. Also, well, we have the enable A and enable B that it's going to be for control the position of the motor. Okay, so we have also this potentiometer that it's connected to the analog in, that is for the A0. Also, well, we have the signal cable, the voltage cable, and the ground cable. So we are going to connect the inputs of the motor to the outputs of the driver, the L293D driver. We are going to connect the 12 voltage here. So also, well, this is going to be need to connect to the ground of something, so it's going to be for the Arduino. We're going to connect the enable A to the pin 9 that is going to send the PWMs. We are going to connect the enable 1 to the pin 5 and the in2 to the pin 7 that are going to let the motor know which direction it's going to be having.
Bueno, como podemos ver, este es nuestro controlador de posición. Aquí tenemos nuestro set point y nuestra posición actual. El set point podemos ver que es de 0 y el valor de la posición real vemos que está variando en ese rango. Ahora vamos a mover nuestro set point con este potenciómetro. Como vemos, aquí se encuentra en 0. Le vamos a mover un poco. Eso es a 90 grados, más o menos podemos ver cómo está, o sea, el set point está más o menos en 90 y la posición real está oscilando entre esos movimientos. Y bueno, le vamos a mover más, 270 grados, y podemos ver aquí que se mueve a 270 grados. Ahora vamos a poner el serial plotter, donde vemos el comportamiento tal cual de nuestra gráfica. Podemos ver cómo ahí está la gráfica oscilando. Y voy a cambiar el ángulo y podemos ver cómo el motor sigue al set point de acuerdo a como yo lo estoy moviendo. Como aquí vemos, tenemos el control de velocidad. Aquí tenemos nuestro valor real de velocidad y nuestro set point. Vemos que está oscilando más o menos en esos valores. Y aquí tenemos el funcionamiento de nuestro motor. Con este potenciómetro vamos a mover la velocidad de acuerdo a lo que queramos y vemos como aquí va variando también conforme se está moviendo el set point. Ahora vamos a ver el comportamiento mediante el plotter. Vemos como su comportamiento es muy apegado al del set point. Y vemos aquí cómo lo podemos manipular, lo vamos bajando, lo podemos subir y vemos cómo se va acercando al valor real. Listo.
For the troubleshooting, well, first we'll need to check all the connections to see if something is wrong, if you don't connect in a great mode. Also, once we check this, we can put the push the reset button in the Arduino just to restart the program and to see if there was something giving any error there. Once you have check this? Well, you can always check that it's connected to the voltage or to your computer. Sometimes happen that, well, you say, oh, why is not working? And well, it's because you have not connected. Also, if that's not the problem, you will need to supply to the motor the boards directly. Because with this you are going to see if the motor is still working or if it have any damage. Also, you can do it with the encoder. You can just turn the rotate the motor as you want, and you will need to see graphic that give you the pulse that it's going the pulses that are going to give you the encoder. And if that's not the case, you can run you can go to the driver that is the L293D driver, and you can put all the voltage together, and to see if the driver is working you will need to connect with a jumper or any cable, just to make the motor rotate to one direction or the other. In the case that it's not working, it seems that the driver is no longer alive. Also, if you already check all of this and it's still not working, you will need to check your program. Okay, most of the times the most easiest way to try it, it's just checking it step by step and trying it in your connection. Okay, so in the case that you already have something that worked and suddenly stop working because you add something to the program, you can check it one again, and in that way you can see if it's working as you think your program. Something important that you need to know is that Euler's formula, also electromechanics and Kirchhoff law, it's important to know because they describe the behavior of the motor, but it's not indispensable for this project. Okay, so you can try it in your house, try with this program that we're going to give you, also the drivers, the motor that you have. It's important to know that motors with encoder have different connections, so you will need to check that before, because just in case to not damage the encoder sensor. Also, some important things in the video that you will need to take in account, it's that you will need to be able to interpret the graphics that we already get here, because to have the KP, the KI, and the KE, it's important. KD, sorry, it's important for you to know which gain modifies what. Okay, so with this in mind, I will encourage you to try it in your house and see how much you understand about this, because also having the gains, it's not really easy, because you need to know some theorems and to have some background to take it, but you don't need to worry, it's not impossible. You can always follow the steps that we have here. That also we already explained it, how we got the gains. About the code, you will need to be able to understand what you are doing in the code, because as we had inspiration for another codes, but in this case we needed to understand what was doing the code that we was seeing, to know which options we need to modify and what of those we can modify, because sometimes if you change something that it's not the right thing, the code will not run in your circuit.